We pretty much take for granted that the things we wear, the things we live with, those things with which we play, and the things we work with, that all these things come in colors. Colors to be had in every imaginable shade, and colors that will not fade or run or come off on our hands. In fact, we've come to take this so much for granted, many of us do not stop to realize that it presents any problem at all. Yet the study of color and light is a science in itself, a science that helps us to understand the appearance of everything around us, from feathers to flowers, from foliage to fire, and from fire to the firmament, the gallery where one of nature's earliest forms of art still hangs, the rainbow. Raindrops hanging in the air separate all the colors in sunlight. This is called a spectrum. And this is the same thing man-made, the glass prism taking the place of the raindrops. But both the man-made prism and the heavenly rainbow tell us the most important basic fact in the study of color, that there is no color without light. So that the color of the screen before you seems to depend entirely upon the color of light cast upon it, starting with violet and going to blue, green, yellow, orange, and red. But is the color of the light the whole answer to the way an object looks? Not entirely, for here is a scene under one kind of white light, and here is the identical scene under another kind of light, but whose whiteness is the same as the first. Here the scene changes in depth and intensity as we move the light. And here the figures appear first shiny, then dull, yet without changing color. So that in order for us to see a color, we need first a source of light, which may be anything from daylight to an incandescent lamp. It is the color of this light that reaches our eye, but it is modified by the object it falls upon or passes through. It may be modified by falling upon foliage, or rocks, or the earth, or by passing through water, or glass, or the atmosphere itself. Each color in the spectrum has its own individual wavelength, just as each note on the piano has its own sound or wavelength. However, you can't play all the notes on the piano at the same time and arrive at anything. But you can take the basic colors of the spectrum and arrive at pure white. From these 5 principal colors come thousands of combinations and variations, shades and hues, all appearing differently under different conditions of light and pigment. Yet that part of the spectrum visible to the human eye comprises only this much of the entire electromagnetic spectrum. That is, of all the forms of electromagnetic energy shown on this chart, these are the only ones we can actually see. We cannot see radio waves, X-rays, radar waves, ultraviolet waves, or any of the others. These wavelengths range from the extremely short ones of X-rays and gamma rays, with wavelengths of a millionth of an inch, to those of the longest radio waves, some of 100 miles and more. However, despite their extraordinary shortness, wavelengths of light can be measured more accurately than any other physical quantity, and this has enabled us to make some headway in the complex study of light and color. As we can see, violet at the one end has the shortest wavelength, while red at the other end of the spectrum has the longest wavelength. We know that all electromagnetic waves, including light waves, travel at the enormous speed of 186,000 miles per second. Let's slow this down a bit so we can see what's happening. But let's keep on assuming the beam is still traveling at that tremendous rate, and in a vacuum or in free space. Because when it suddenly has to pass at an angle into a transparent material, like water, the direction of the beam is changed, like this, since it is slowed down considerably by the denser medium, so that the light beam is actually bent or refracted when passing from one medium into another. And this is why an object seems to bend when placed in water. Its direction seems to be altered. The lines on a printed page appear to be in a different place when seen through a piece of glass like this. But the bending, or slowing down, is different in this medium. The amount of bending or slowing down is called the refractive index of the given material. Yet this isn't all that takes place. We also get a reflection of a portion of the beam. This happens whenever there is a change in index from one material to another, in this case, from the air to the glass. Here, with ordinary glass, approximately 4% of the original beam is reflected from the surface. That is, the light is reflected in one direction, like this, but only when the surface is smooth or glossy. When the surface is rough, however, the reflected light is scattered in all directions because it is hitting that many more individual surface angles. It is this understanding of the basic behavior of light when it hits an object that underlies all our knowledge of industrial finishes, lacquers, textile colors, printing inks, and all forms of chemical coatings in art and industry. These materials are all basically composed of a vehicle, or liquid, in which are suspended innumerable fine particles of an insoluble substance, sometimes called a pigment. Let's say our vehicle is linseed oil, and our pigment particles are made of the same glass we have seen, ground into a fine powder. We now have the ingredients for a basic form of chemical coating, that is, a vehicle in which pigment particles are suspended. The coating can now be applied to a surface in a thin layer, as we do with paint, for instance. But the story only begins here.